today the topic is on Hamiltonian dynamic simulations using linear combination of unitaries on a quantum computer. This is largely based on our recently posted paper in arXiv. And did I not do that? Okay, hang on. Sorry. I thought I did that. Okay. Can the people online see my? Okay.
With your non-projected screen. So if you just maximize it, it would.
Yeah, we see the.
You see the. Okay. Cool. Okay. Yeah. So by Hamiltonian dynamic simulations, what I really mean is taking we've only gone as far as taking the squared overlap of an initial state psi naught and a final state psi f, which is a time propagated initial state. And given this Hamiltonian of the system. Okay. Also, the main actor of this work is the linear combination of unitaries, LCU for short, which is literally linear combination of unitaries. So here, to simplify things, we assume that the unitaries are Pauli strings, but in general, it can also not be Pauli strings. And so here in this expression, we have L terms or n unitaries. Epsilon is the overall sum, and alpha not the alphas are the coefficients, can be complex in general, but in practice we absorb all the phases into the Pauli strings. So LCU is really all about finding a circuit representation for something that may not necessarily be a unitary. Okay, just to set our expectations from this talk, there's not much chemistry. I know this is a chemistry seminar, but there's probably no chemistry at all, but the methods that I'll be discussing may be applicable to your problems solving. And then second is, I would like everybody to understand LCU. I mean, that's the minimum requirement. And it would be better if you can also recognize how and when it can be more advantageous than Trotter. So, okay, so also in the context of Hamiltonian dynamic simulations, we usually hear about LCU in terms of complexity theoretic studies, although it may scale asymptotically better than product formula or Trotter, it is rarely implemented in practice because of the overhead cost. So at the end of this talk, I would also like to talk about how we are able to implement a small LCU algorithm in our ion trap machine. Okay. So I thought to better understand LCU, we have to start with a very small example, which is a linear combination of unitaries. So here we have x plus y. And as you can expect, since an LCU may not necessarily be a unitary, we may need to use an ancillary register for this. So in general, the algorithm will make use of at least two ancillary registers, one to encode the coefficients and the other for the system for the system itself. So the ancillary register, we denote that as the P register, will initialize it to 0 qubits. And also so you have the psi register or the Q register for the system. So here, since we have two unitaries, your ancillary register will only have 1 qubit. Okay, so the problem is really finding a circuit representation for this walk operator W. Okay, so first we encode the square root of the L1 normalized coefficients in the ancillary register. So we can do this by using this rotation gate or RY gate given by this expression. So if you do that, your your system state will remain unchanged, and then your ancilla now will have this square root of the coefficients. Okay. And then we perform the unitaries corresponding to the controlled by the ancillary register, which correspond also with matching where the activated bit string is matched to the Pauli string. So for example, here, if we want to perform the x term, we set since the zero ancilla state here corresponds to the x operator, then we have the control here as the null control. And then for the y, we have the one control since the y operator corresponds to your one ancilla state. So that's the second part. And then in an attempt to convert back the ancillary register back to the zero state, we have to do some uncomputation by doing this inverse of the RY gate. But doing so, we find that, it's not always going to be zero state. There's also the one state. So eventually we have to do some post-selection. Since the desired LCU that we want is in the zero state, we have to post-select the zero state from the ancilla. Okay. That's that. So this is your circuit, or this is the LCU circuit for given that LCU. And so if we scrutinize this operator further, these without considering the states, we find that there will be like 4 sets of operators without the post-selection. So the 0, 0 block will correspond to the LCU, the desired LCU. The 0, 1 block will correspond to this, and then the other off diagonal will correspond to this, and then you have the 1, 1 block. So these are all irrelevant to us. The non-top left corner. And I hope you can see now why LCU is like they call it a block encoding method. So you're encoding your LCU on the upper left corner of your bigger unitary. Okay, so to generalize and summarize, so for example, we have LCU terms, then we always have at least 2 registers, one for the system register Q, the other one is the ancillary register. Your ancillary register will have log L qubits, and then you have the prepare oracle, which prepares the coefficients, the L1 square root of the L1 norm of the LCU coefficients. And then you have the select operator. It's a multi-control operator that performs the unitaries in your LCU. And then you have the unprepare oracle. And then towards the end, you have to do some post-selection since we're only concerned with the one block of that larger matrix. And then, so the next question is, how often do we project to that upper left corner or to that block? The answer is this expression. So it's the success probability of LCU is inversely proportional to the square root of the L1 norm of your coefficients, and then also with the initial state, and then this the LCU itself. Yeah. Okay, so this is just a matrix illustration of LCU. So, sorry, if I meant this talk to be also pedagogical, so if you have questions, please feel free to raise them now or later. I'm fine. Yeah. So what's inside the prepare oracle is a big body of research in itself, but naively you will have like control gates, rotation gates and multi-control gates. So here in our work, we use the multiplexor synthesis. I won't go into details because it needs some time to absorb it, but note that with this multiplexor synthesis, the number of CNOT gates to perform a prepare oracle will be given by this expression, which is about 2 raised to the number of qubits in your ancillary register. Okay, and for the select oracle, so naively you will have this multi-controlled gates. And then again, if we use the multiplexor synthesis, the number of CX gates or CNOT gates will be equivalent to this expression. So 2 raised to the number of ancilla qubits or control qubits times the number of qubits in your system register asymptotically. Okay. Okay, so going back to the Hamiltonian dynamics problem, again, I'm just repeating this slide here so that we recall what the main problem is. So what we did was we Taylor expanded this time evolution operator by first splitting or dividing the time into m steps. You have to do this because we're going to truncate this Taylor expansion at some point without having a small time parameter here. The cutoff here will be very large. So this small time here is necessary. And then the term inside the square brackets are actually an LCU in itself, but we also expanded that. So if we raise this square bracket into m steps, we classically expand that further to get a bigger LCU. So at the end, we only have a single LCU representation for this time evolution operator to make things simpler to implement.
So you expand that Taylor expansion out all the way up to m as well.
Correct.
And that's probably going to be the largest term in there. But then can you resum anything in there, or is you just got to take each of these?
Okay, so the assumption here is that you can classically do this, but it's not always easy. So for small systems, if you sum it, like there will be cancellations in terms, and then you will also have addition. So sometimes it may collapse the number of terms in your LCU. So yeah, so did I answer your question or?
Anybody operator, which is
It will be challenging. So another method to that is before expanding. So for example, you have before expanding to the so let's just say this term inside this, let's just say it's some u. So before taking the u squared, one can actually truncate that so that the higher order terms or the terms with correspondingly small coefficients, you can ignore that and multiply that. And then you can keep on ignoring higher order terms as you recursively multiply to higher m. Reasonable for smaller systems and for not so large m. But I admit it, even I tried to do for like m greater than 10, or I think at most I was able to do up to 14 with like the Paulis are in the order of only 10. The system has 10 qubits, so it becomes challenging as you go to higher m and also higher number qubit system. Yeah. So this is not really for a long-term or fault-tolerant quantum computer, but yeah. So, okay. Here, yeah, okay. Okay, assuming that we can do that, like we can classically expand this exponential of negative IHT, and then we get this LCU. What we did was we divide the resulting LCU into two groups. One group, we call it the parallel group, and the other one is the orthogonal group. So what we mean by parallel group is the operators in that LCU where if you act that on your initial state and then take the overlap with the initial state, it will give you non-zero. Whereas if, on the other hand, the orthogonal group will give you a zero overlap with the initial state.
And that's relatively easy to do it through symmetry in some cases.
Yeah, so one should always consider symmetry to make your life easier. It helps.
Some of the operators split between the different groups. If you accidentally have some operators in Y parallel that are...
No, it doesn't matter, but it will just increase the cost of your implementation. Okay, so for example, also the assumption here is you know your initial state. And your initial state will always have symmetry since we're considering some physical system, right? So it won't take all the possible states in your Hilbert space. So for example, here your psi naught is given by this 4 basis states. Then the terms here in the perpendicular space or group will give you a non-zero overlap. So for example, if we act this on this state, it will give you a non-zero overlap. Whereas if you act these operators here on the right, it will give you zero overlap. So I, Y, Y, Z won't have a corresponding state here if you act this in any of these bases. Okay. Okay, so I hope you can see where I'm going with this. So our proposition is we only do LCU on the parallel group and ignore altogether the orthogonal group. But there must be some trade-off in doing that, right? Since you're ignoring some terms and then you have to do some renormalization towards the end. So here I included the derivation to how to get that renormalization factor, and also to convince you that I did my assignment. You can do this too before you go to bed, but it's simple. But anyway, the bottom line is there's this renormalization factor where here the numerator is related to the success probability of doing the parallel group LCU times the L1 norm squared of that LCU. And the denominator is approximately equal to 1, since the operator we're considering here is the time evolution operator. So we approximate this to be equal to 1. So what I'm saying is that we do LCU for this, and by doing LCU, you will, automatically know what these are, what these success probability and the L1 norm of the coefficients. And then from there, you can process the data and then obtain your desired squared overlap quantity.
So if you hadn't done that separation, you
Mhm.
would have got hopefully the same answer. But the reason you do it this way is because the measurement of that last overlapping expression, it has a higher success probability, which you then rescale down effectively to.
One can think of that way because, okay, so by reducing the number of terms in your LCU, you're also reducing your L1 coefficients, right? So it will actually kind of boost your LCU implementation. Okay. Yeah, so and then we test this method for a Rabi-Hubbard Hamiltonian. So a Rabi-Hubbard Hamiltonian. So this is the simplest case of a Rabi-Hubbard Hamiltonian where you have, it's a light matter interaction Hamiltonian. Here, I only considered 2 cavities. So omega c here is the angular frequency of your cavity or your photon. And then there is some matter. So which is, or we considered it as a 2-level system atom with a frequency omega A. And this is the Hamiltonian of the system. So this is for the cavity component of the Hamiltonian. This is for the atomic component. This is the interaction of the cavity and the matter or the atom. And then there's this hopping term where the photon can actually hop from one cavity to the other cavity. So J is the hopping strength of the system. And for since the cavity is considered to be a photon, like it's a photonic system, it has, in principle, it has, it can go as high as, 100 modes, since you can consider it as a boson, so it can really go up. But here we're only considering at most 2 photons in a cavity, so we put some cutoff to that. And for this A or bosonic number operators, we use the binary encoding.
Fermions without any minus signs, because you can only have 1 or 2 of them in each.
No, so what we did here was it's, I wouldn't say spin half, more like, for example, if you're considering 1 photon, you literally set that as 0. So for example, you have at most 3 photons. So you indicate a 1 photonic state as 0, 1, a 0 photonic state as 0, 0, a 2 photonic state as 1, 0, so in binary form. So yeah, so the spin really here is really irrelevant for the encoding.
Directly rather than create an extra photon.
So A dagger, A is a number operator. So you're kind of create.
If you apply a dagger to the vacuum,
what
what happens? Is that so?
It gives you 1 photon. So, but since I set the maximum number of photons here to 2, I think, or 3. So if A dagger acts on the maximum photon that I set state, then it will give you 0.
Okay,
Since
but
I have
take
that. Correct.
So it's
Find its binary.
is I indexing the cavity, which cavity it's going into?
Yeah, correct. Yeah, that too. Sorry for the confusion. But also you should know that I set some cutoff to the number of photons the cavity can contain. So that also affects the Hamiltonian. Okay, so I set, so per cavity, I said that I set it with at most 2 or 3 photons. So that means it will make use of 2 qubits, right? For the photonic component of the state. And then we also have the atomic component, which is, or we consider it as only a 2 level. So 1 qubit state for that. So each cavity can have 3 qubits. So, but you have 2 cavities. So in general, you will have 6 qubits in your system register. Okay. But in this implementation, we also did some qubit tapering technique to cut down the number of qubits. So eventually we're able to cut it to 5 qubits for the system. And so these are just the details. There are 49 terms in your Hamiltonian. After transforming this Hamiltonian in qubit operators. And then if we do the Taylor expansion and truncation of the time evolution operator, you will have 400 to 500 terms. So this is like 8.
What m did you use?
Nine.
How many terms in your Taylor expansion?
So I set my truncation order to 8 here in this example. But in general, I ignored all the terms with coefficients corresponding to smaller than 10 raised to the negative 8.
So you just kept doing.
Yes, correct. Yeah. And my initial state is set to the Mott insulator state. It's okay if you don't understand this, but I just put it here for posterity. Okay, and then if we do this, the splitting of the parallel and orthogonal groups, then I find that there are at most 15 terms in the parallel group out of this 500 terms. So this is a huge reduction. So I said here at most 15 terms. This is across different times that I considered in my simulation. Okay, just for a sanity check, I checked this expression here. So I plotted this, the left and the right hand sides of this equation by, the assumption here is the denominator is equal to 1, since this is almost equal to unitary. So they agree. This is all state vector simulations. Okay, so before proceeding, I would just like to include the vacuum, the circuit that I used to get the squared overlap. So we're only taking the squared overlap of the initial, the squared overlap of the initial state, and then this reduced LCU, epsilon parallel operator acting on the synod. So this is in effect your final state here. So to take the squared overlap, we prepare the synod first by having this state preparation box. So
you can't evolve into any space that's perpendicular to your original state.
yes, after doing the splitting between the parallel and the orthogonal group. Yeah. We've already assumed that we've done that.
So you're assuming that.
Yeah. But later we have to do some renormalization factor. or renormalization. So here we're only doing the reduced LCU squared overlap. And then you do your LCU for this operator. So you'll evolve to this state and then do this unprepare again to get your squared overlap. So, okay. Any question here? This is just a diagram, not really a detailed illustration of what's happening inside, but this is one way to do your squared overlap, but you can do Hadamard test or whatever tools you have. So we use this because this will kind of reduce your qubits, and because in the Hadamard test, I think you have to have another register to prepare your final state.
Post-select step, but just acting on the ancillary step. I can't quite see.
And the state.
And the state too.
Okay.
Yeah, correct. Okay, here are the results. Sorry, this slide is a bit busy, but we'll go to it one by one. So, okay. So what we did with in our simulations is we computed this squared overlap. This is this reduced squared overlap where we considered only the parallel LCU, right? So in each plot, I have the state vector result. Okay, the x-axis here is the time axis. So this top part here is this squared overlap of what we actually implemented on the quantum computer. It's a reduced LCU. And then we also considered the emulator results, the noisy one, and the mitigated results, and also the actual hardware results. So, okay. So the noisy one is really noisy. And then what we found out is that what the main factor or the main contributor to that noise is the memory error. You can think of the memory error as the error incurred by those idling qubits. So idling qubits are those qubits that are not doing anything while the other qubits are doing something. And one should expect that from LCU because of the architecture of the algorithm, right? Yeah, so we mitigated those noises by doing some dynamic decoupling. So we inserted pairs of X gates on those idling qubits so that they wouldn't be idling too much. So that's how we mitigated that memory error.
Could you try and parallelize some of your application of the Paulis? Because you might have been able to do that at the same time, or were you just sort of taking them one by one, and that's why you had lots of idling qubits?
So this is already like compiling it optimally.
Okay, so you compile it off.
Yeah.
They're still idling.
Yeah.
So at that point you can.
Yeah, correct. Okay, so these are the results from quantum computing. The squared overlap results of the reduced LCU, and this is the success probability of implementing that LCU. And then we have to post-process it to get the actual squared overlap that we're after. So the only factor that you'll need is really just this success probability. The L1 norm coefficients, you know that already, right? So we post-process these data and then to obtain this plot that we're really interested in. So this is this bigger plot here.
That's a renormalized thing.
Correct, yeah, correct. So yeah, it's not a bad, I would say. I know as not as bad as it's a weak statement, but I think it's not wildly divergent from this state vector result or the
So,
ground truth result.
Would you not, I suppose, expect the noisy ones to be more over the noisy emulator to be more like the actual H1s, because the state vector won't have any noise. So
The H1's also mitigated.
Yeah, so
Mitigation,
yeah.
yeah.
So the H1, the hardware results, we also mitigate that already. So what we run in our hardware is the circuits that where we also included the dynamic decoupling mitigation protocol. I think this is just system dependent. So, and given these parameters, so I think for
The oscillation.
yeah. So for different parameters here, for a different J in particular. I kind of lost you there. So sorry.
I thought that
Not always. So the success probability of LCU is dependent on your initial state, your operator, here the reduced LCU, the epsilon parallel, and also the coefficients, inversely proportional to the L1 norm of your coefficients, right? So there are at least 3 factors contributing to your success probability.
Why do we want to know this overlap between the initial states and the state after the time inclusion?
So for this particular problem, so this is more like a physics problem. They use this to observe some phase estimation, phase transition. So they observe at which value of J or G a phase transition may occur. Yeah. So, okay, can you?
like these overlaps. Nice.
Sure. Yeah. Yeah.
Mhm.
Yeah.
Yeah, I mean, yeah.
But yeah.
Yeah, so
Is it necessary to take the overlap with the initial state? As in, like, you couldn't just work with this generic state?
Yeah. I mean, it doesn't have to be the initial state as long as you can prepare that state, right?
I mean, this is also experimental observable. Experiments called the Loschmidt echo experiment.
That too.
You can measure how far away the final wave functions from the initial wave function. It's very much used in condensed matter physics.
The success probability depends on the overlap between the initial state and final state that you're projecting onto. If that overlap gets high, your success probability could also get high. Yeah, I think I was confused. I said it was overall success, like the sum of all of those.
yeah, because you're doing separate circuits for every
Yeah.
time.
Yes, you circuit for
I
each.
got confused. Yeah, I see.
Yeah. Okay. Sorry. You will always have different. So the x-axis here is time. So you will have different sets of epsilon parallels for every time in your time grid. Okay. Sorry. Yeah. Okay. So after post-processing these two sets of data, you will get this actual squared overlap.
Sorry. But if you did a range of measurements, could you do some sort of shadows thing to do a tomography of the state, final state? Or is that not possible?
Okay, I don't know much about shadows, so
Yeah, but if you measure below that a lot of observables, then if you did a lot of different states.
But because it's LCU, it's one of the same circuits.
Well, but yeah, that's only, you're not starting from multiple, right? Like you could do different
It'd be
stuff.
the same initial state, but it would just be a different parallel every time. Yeah.
Yeah.
It's just need to do it different. Yeah, different Hamiltonian basically.
But then you'd be applying different Hamiltonians, right? And what would that tell you across the state?
So you have to pick that much only based on the actual state. Okay.
Who knows?
Yeah, I don't think that's meaningful in this case.
But I'm glad you're thinking about how where you can apply this. Yeah. Okay. Okay. So the resources that were used in these experiments are included in this slide. So 9 qubits, so 5 for the system register and 4 for the prepare register or the ancillary register, since we only have at most 15 terms in the reduced LCU. Also here, the depth and the 2-qubit counts are almost constant throughout time. And I think a lot of comments that I get here is that this is too good to be true, because usually if you propagate your system to longer times, your resources will increase as well. Like for example, in Trotter, I think the scaling is t squared, or yeah, at least t squared. So here, what made this possible is that we were doing the classical expansion of the whole time evolution operator before doing the quantum computing implementation. So that's how we got away with this. Yeah, so I think I'm at the end of my talk. So to summarize, we have demonstrated our LCU implementations in our ion trap device for calculating squared overlaps of the time evolved states, and then coupled with multiplexor gate compilation strategy, significant reductions in the circuit resources is observed after applying our reduced LCU method based on pre-selecting the relevant unitaries. Yeah, so we have the data in this GitHub repo, and please do check our paper if this interests you. Thank you.
The resource counts.
Mhm.
Are they being constrained by the size of the Hilbert space here? In that, if I do my classical expansion up to a certain level, I'll truncate when I hit the maximum depth of my Hilbert space.
Yeah, so here, the truncation that we did here was really just based on the coefficients of the LCU, right? So what's not constant here is the error that I accumulate by doing that truncation. So I can show you. Sorry, I'm a bit digressing to what you're asking, but so for example, as you can see here, by setting k equals 8, or the Taylor truncation order to 8 across different times, we're getting this error, which is not constant.
Relatively small number of possible poles.
For this size of a system, I'm not running out of Pauli strings. It's just that they only have minimal contribution to the overall. But for a small system, let's say if you have like a 2-qubit system, it's easy to exhaust all the Pauli operators. Actually, I have a plot here. Yeah. So for example, I think I've tried, so L here, so here L is the number, L sub H is the number of terms in your Hamiltonian, and the one on the right is the number of terms in your propagator. So for these data, I think, at least for the first data, I think, no, I think this is still too big. But I've tested it for a smaller system where, you know, even without truncation, even going to higher K, the number of terms in my time evolution operator remains constant
Yes.
because you've exhausted all the possible Paulis, right? Yeah. I only use the one that's in Encanto, but it's largely based on the IBM's qubit tapering protocol. I think they wrote a paper on that, and I think Encanto is also based on that protocol. Okay. The principle behind qubit tapering is also symmetry. So if the general idea, if there's a qubit, or yeah, if there's a qubit there that it can remain constant, or there's some symmetry, then you can always just ignore that particular qubit with some transformation before reducing your system into a smaller number of qubit. Yeah, that's the general picture.
Possible that you could have, maybe not in this Hamiltonian, but that if you want to go to very long periods of imaginary time, or no, long periods of real-time evolution, your classical process becomes intractable or something. I mean, because that's going to be, yeah.
By classical process, are you referring to
The construction of the
yeah, I think you're referring to what if we have higher M in this, is that?
Yes, yeah.
Yeah. I think,
because you can use the truncation, but at some point you might end up having things that reaccumulate and add together, and there will probably be, with the right Hamiltonian, a period which you end up back on the original thing together.
Yeah.
And depending quite how you're doing your truncation, you might end up throwing all the things away, so you never get that.
yeah. So my answer to that, on the safe side, is yes. This is not, the method here is not highly scalable because of the classical part of this method. But yeah, this is for like early fault tolerant implementation. But there's also no stopping you from, developing an algorithm to make that classical expansion more efficient.
So you said the bottom of your fraction, did you approximate it as 1 in the numerics? Or because I think you showed a graph
Yeah.
two slides ago or something.
Yeah.
You plotted it. Was that with the
I just set it. Yeah, I just set it to 1. Is this the one? This one.
Yeah, you showed a plot of the error, which had like square root.
Okay. Yeah, I remember.
Yeah.
I think that one's for the full thing. There's nothing.
Yeah, this is for the full thing without doing the splitting yet, without doing the subdivision. So this is an error plot for doing that truncation, Taylor series truncation, but not for the yeah,
So
correct.
basically, this is the plot of proof that you relative to one is
Kind of, yeah. So this is proving that for k equals 8, if your k is equal to 8, then you're close to actually getting that time evolution operator at different times. the face. Okay. It is definitely interesting, but how to do that here? Sure. Yeah. Yeah. Yes. Yes, definitely. Yeah. Mm-hmm. Yeah, correct. Yeah. Correct. Did I don't have it here. I don't know on top of my head, but sorry, I don't know. But I thought that I actually checked that how one should truncate that k given the system qubits, the number of system qubits. M, correct. Yeah. M is the number of time steps, right? Yeah. Here, no, but you can actually set that M based on the error you want to target. Yeah. So the way people usually do it, like those complexity theory studies, what they find first is the error, how the error will affect the truncation cutoff. And that's how they set their K. And then you have to know how small, also, it will also depend on that small time parameter, right? So that's where your M comes in.
Maybe in that case, actually, this it's more that this process of projecting out the picture actually gives you a better reduction because you would have had more zero terms that you can't throw away below the threshold.
Mm-hmm.
Like if you have a lot of terms that's similar magnitude
Uh-huh.
and you have to go by order of k, you still end up with a lot of terms that you can't throw away.
Yeah.
So then maybe the relative difference when you project out things that are quite symmetry is bigger.
That's possible, but probably here it's just coincidence that, not everything goes into that parallels group, right?
Yeah.
You can produce a, also equally large magnitude LCU or unitary, but that will end up in the orthogonal group. Is that?
Yeah. It depends.
It depends on the initial state, correct? Yeah. Mm-hmm. Yeah, correct.
Guarantee that I can take this between the parallel ones and its orthogonal projection. This exists because I always have a projector and its orthogonal complement. Is that right? Like, why does this decomposition always exist? I just want to be clear.
Well, what else could happen?
So it's either 0 or not, I suppose. No.
It's not guaranteed to be an empty then.
Not
Well,
guaranteed,
it's
it's
not
not guaranteed.
guaranteed to be, yes.
Okay. Yeah.
So that is the orthogonal
And
complement.
if you start with a completely mixed initial state or something, you make any zeros.
Correct. If for example you have like n-qubit Hilbert space, usually your initial state, if you're considering a physical system or non-physical system, it can have as large as 2 raised to the n number of basis states. But since what we're considering here are physical systems, then you're
Oh, it's the
Um,
multiplexor state.
yeah, it has some symmetry.
That's
Yeah, yeah, yeah. It's a superposition of
So it's called like
um I don't know what the Neil state, but a Mott insulator state is a superposition of, for example, we have here atom in the cavity state, right? So if it, possible state is if your atom is in the ground state, your cavity is in an excited state or non-vacuum state. So it's a superposition of that pair and a pair where you have a vacuum state photon or cavity and an excited state atom.
Yeah.
So that's a general description of a Mott insulator state.
So only one of the two is excited in any given
Yeah,
term.
but then it's a
Yeah,
superposition.
superposition of
Yeah,
all the options, but
yeah, correct. Yeah.
And can your multiple photons?
Yes, it's this is the way I cut the number of photons, I think, into at most 3 or 2. If you set a higher cutoff to number of photons, then you will make use of larger qubit numbers. And also here, I only considered 2 cavities. So,
If you're
you can too. Yeah.
or up to your cutoff. but
Yeah, yeah,
the
yeah.
Mott insulator state will include states with 2 photons and with 3 photons.
Yeah,
and
yeah, yeah.
Thank you very much.
Thank you.